Hello, everybody. This is another episode of our podcast, Artificial Intelligence and Cybersurgery. This is the official podcast of our journal, Artificial Intelligence Surgery. I'm Dr. Andrew Gumbs, editor-in-chief of the journal, and I will let my co-host, Dr. Vincent Grasso, who recently became a research professor at the University of New Mexico. So actually, maybe, Vincent, you can tell us a little bit about that before you introduce our next guest.
Absolutely. No, thank you. And it's a pleasure having Jerome on, which we'll introduce shortly. So I have the great pleasure and privilege of being a research professor now in the Department of Electrical and Computer Engineering at the University of New Mexico. And shout out to Professor Marios Patichis, who sponsored me. And we'll be doing, all of us will be doing some very interesting work out of there on the technical side of our project. So great for us all, and great privilege, and I'm very appreciative. I have the great pleasure of introducing Jerome Jackson. So this is a very interesting non-physician, Andrew, right? We have, most of the times we have surgeons on, but Jerome is a very interesting guy. He comes out of Stellar Tech, I believe is the correct name of the company, a very interesting R&D company. Jerome is an engineer too, so he's a mechanical engineer with some serious credentials and patents, and working on, I guess, medical devices and such for quite a long time. So welcome to our podcast, and let's learn for our audience some more about you, Jerome.
Thank you for what a great introduction you just provided, and for inviting me to your show. I'm really honored to be able to participate in it. As you mentioned, I'm Vice President of Research and Development for my company, Stellar Tech Research. I've got a long history and background in the medical device field. Actually, you mentioned my degree in mechanical engineering, but my undergraduate degree, which I got from Harvey Mudd College, is actually in engineering science. So it's a blended engineering degree. It involves electrical, mechanical, computer science. And my terminal degree at Stanford was mechanical, but I continued that tradition because, as we all know, biomedical engineering is really a combination of all the technical disciplines: computer science, mechanical engineering, electrical. And so you really need to be facile in all these technical disciplines. I've worked in this field for a long time, about over 40 years. So I've worked in,
Wow.
I know it's been a while.
Really, whatever you're eating, please maybe tell our audience member what the secret is. But Jerome, if you don't mind me asking, where are you from originally? You're originally from California?
Yes, I'm originally from Southern California. I actually grew up in Los Angeles, and I call it the real Los Angeles, South Central Los Angeles.
So Lakers or Clippers?
Lakers. I grew up as a Lakers fan, but I've actually been in the Bay Area for a long time now, so I'm a dedicated Warriors fan.
Oh, good. I approve. So tell us a little bit about Stellar Tech. I mean, I just recently got to know your company. You know, you obviously know that we reached out to you to help us develop a device. But I was just thinking Stellar Tech, and actually looking like you, I must say you look a little, you remind me of some characters in a superhero film where you're the benevolent genius working for this big corporation, and it even would sound something like Stellar Tech.
Yes. Well, I appreciate that analogy or that allusion. We try to stay humble, but I really feel grateful to be able to participate in the field at this level. Stellar Tech's a very different company. We don't manufacture products for ourselves. We actually do it for our clients. So you'll never see a Stellar Tech research product, but we develop products for a range of clients, all the way from startup companies, venture capital-backed companies, many of them without even a company headquarters, all the way up to Fortune 500 companies. We pride ourselves, though, on being able to integrate these technical disciplines to produce the precise clinical result that you're looking for. So the best model for us is that we partner with physicians very early on in the process, and we get from them very specific details about what are you trying to do? Are you trying to produce a change in tissue? How much of a change? What's the size? What are the tissue layers involved? How deep do you want to go? All these characteristics that you would like the treatment to reflect. And then we'll engineer the system all the way from the capital equipment, the patient contact device, if it's got an electrode, the electrode that interfaces with tissue, and we'll optimize that and produce precisely that result. So we understand, electromagnetic theory, interaction of energy with tissue, how to control these parameters in order to produce precisely the result that you're looking for.
So as I mentioned, my VP of business development knows you for many years and reached out to you to help us develop this device. But I must say I was so impressed with your company because, even I, as a surgeon who uses technology, who uses things like electrocautery and bipolar devices, I didn't realize the degree of sophistication that is required for regulatory approval, and it was such a wonderful surprise to me to find out that there are companies that they devote specifically for this. I mean, this is so it's such a shame I didn't know this in medical school, that I could reach out to someone like you to help me maybe do a procedure better sooner in my career.
Oh yes, as you mentioned, I think this is the ideal relationship, that we partner directly with the interventionalists that are performing the procedure, surgeons, whatever, the ones that are actually going to do the procedure, and if they can convey to us, and in some respects that's my job, is to have that dialogue with the physician and to take their description of what they're trying to produce in the tissue, the result they're trying to achieve, and then translate that into engineering terms and ultimately into a system that will provide that function. So that's a perfect marriage, if you will. Right.
And how do you get exposed? Like, are you taught anatomy or pathology, or how do you learn the various tissues, how to analyze, interpret what your machine is doing?
Well, interesting you asked that question. I had that question to myself when I was going through engineering school. And what you find is that the best preparation for a career in biomedical engineering or medical device development is a solid engineering background. I don't need to be a physician. I want to pair with you as a physician to find out what the requirements are. And so a lot of that I actually, will learn from that interaction. Now, as a free elective going through my master's program, I actually did take anatomy and physiology and some courses directed towards biomedical instrumentation and measurement. So that did help. But the fundamental requirements were to be a good engineer and to master that and to rely on my liaison with medical professionals to learn the details. Now, in addition to that, we will do simulations, right? We'll do things in the laboratory to simulate the actual tissue effects. And so we do learn quite a bit more there.
Just, sorry, I was interrupting you, but do you partner with a pathologist to interpret some of the images of tissue after it's treated, or how does that work?
Oh, absolutely. So what we do is we develop progressive models. So once we understand the desired effect that you're trying to produce in tissue, then we'll develop in vitro models. The very simplest ones might be, as you know, resistors or networks, capacitor resistor networks or something like that, just to show that the system is delivering the proper parameters. And then we'll find tissue analogs. Now, these are already butchered or dead tissue analogs. So we can understand the interaction of the device with tissue. We'll try and emulate the temperature characteristics and the coupling characteristics, and we'll produce what I call sort of gross changes, but those are not really pathological changes. Those are just the effects of heating tissue, and we look for blanching or things like that that are pretty gross results. Then after that, we go to the next progressive model, which is animal testing. And there we'll try and test the actual tissue that you would treat in a human. And at that point, then we'll send those samples to a pathologist, and they'll do both gross and histologic assessment of the tissue. We'll look at what tissue layers it involves. Is it going too deep? Is it going deep enough? Is it affecting the right cells? And those sorts of things. And then we'll submit that data to FDA, and at that point, then we'll go to human clinicals.
That's fascinating. I cannot tell you how exciting it is to work with you. Obviously, we can't talk about the product that we are collaborating on, but I did want to ask you: have you known Stephen Song for a while, or did he know maybe more one of your business partners, or how have you known him?
Yeah, he knew one of our business partners. I believe it was a company called Bayless Medical that did a device to cross atrial septums. I believe that's where that came from. But we've been so prolific in so many products that we've crossed paths with many customers.
Can you give us an idea of maybe some of your favorite products that you've worked on? You don't necessarily have to give us a name if you don't want to, but maybe a pathology that you particularly find interesting to work with, or some insight there?
Sure. I actually have one that's really pretty interesting. And it's public, so we can talk about it. But it was for a company that we actually incubated in Stellar Tech Research, and this company was called Barracks Medical. And it was a device to treat intestinal metaplasia, which is really in the esophagus when the cells that line the esophagus get replaced with those that look like cells that line the stomach because of acid reflux. And when we developed this product, they weren't treating this disease. They would just do surveillance endoscopy every 3 to 4 years. And if the patient didn't have cancer, they'd say, come back and see us in a few more years. And we came up with the idea, working with a physician, obviously it was led by a physician, but what happens is you could put the patient on what's called a proton pump inhibitor to suppress the acid reflux, but the tissue wouldn't revert to its normal morphology. So you still have that precancerous tissue there. And so they said, if you could treat this tissue, if you could remove that layer, then we think the normal esophageal mucosa would repopulate. But if you go too deep, you'll give this patient a stricture, and now they won't be able to eat, and you've made their condition worse.
Right.
So we developed this bipolar electrode array. I actually did the finite element analysis to look at the electric field depth, and we came up with an electral pattern where the depth of the electric field, the majority of that energy attenuated within about a 1/4 millimeter of the surface. So when we delivered that therapy, it would go from 1/2 to 1 millimeter deep into the tissue, including conduction, thermal conduction, and all the secondary effects. So we were able to totally ablate that superficial layer of Barrett's mucosa, not affect the muscularis, and heal that patient. So this procedure went from from one that was never performed, they would never intervene, they would just do surveillance endoscopy, to now this is highly practiced and in many centers has become the standard of care for treating Barrett's esophagus.
No, absolutely. We know it very well. It's fascinating to know the origin of it. Amazing. It's Vincent knows my brother-in-law and my nephew. And actually both my brother-in-law, who's a surgeon, and myself, we're so happy to find out he's actually going to become a mechanical engineer. Actually, we want to create him. We're very happy that he's not becoming a physician, is what I'm trying to say, because I think impact people. You can end doing what you do. You can impact many more people. A surgeon can impact one person at a time. If you develop a new technology or a new device, you can impact innumerable amounts of people. So it's a very rewarding field. But I digress. and we're getting on in time, and we have to touch upon a little bit on artificial intelligence. So can you tell us how artificial intelligence has impacted how you do things?
Sure. The biggest impact, I will say, is in analysis of the parameters that are associated with energy delivery in order to predict how the procedure is actually progressing. So, and so in this area would be essentially using the linear regression AI type routines in order to develop associations between the parameters associated with energy delivery. So many times we'll look at the voltage that we're using to deliver to an electrode to produce a therapeutic effect. We'll look at the current, we calculate power, we calculate impedance. But in one such application, even though we know these parameters, and this is a device where we actually generate steam to produce the therapeutic effect, the thermal therapeutic effect, all those parameters actually won't tell you when you're actually developing the therapy. So we actually used artificial intelligence to analyze these parameters and come up with relationships between them that allowed us to predict when this therapy was being effective. So that's where we're using it. Now, we sort of use it in the analysis of the data sets to program the response. So it's less of it automatically doing something, but we do program the system based on the result of that analysis.
I mean, I just love that because, you always hear about people worried about artificial intelligence. There are all these, we see daily somebody's worried about our AI taking over the world or what have you. And,
Yes.
and personally, that's fine in that world. But man, do I love artificial intelligence in healthcare. I mean, I think it should be completely unleashed in healthcare. Just like you say, you're able to develop a treatment algorithm that maybe otherwise we wouldn't be able to devise is just such a wonderful example of the power of AI in healthcare. I love that.
Yes.
Yeah.
So it's
So,
been very effective and very accurate. So we appreciate it, and of course it'll expand more. We're just sort of at the frontier of implementing this type of technology in our product development efforts.
so Vincent, you're now going to have access to some of the most powerful supercomputers in the United States, possibly or probably in the world. How can you envision working with someone like Jerome?
Sure. No, this is so exciting. I mean, Jerome, the all the simulation and modeling that goes around assessing energy transfer in tissues is computationally intensive, right? So that's very interesting. Do you guys use is MATLAB one of your platforms to crunch your numbers, or what do you use to do a lot of your simulation work? Do you have any software that you like, or do you find any technical challenges? The data sets are getting so big that you're having issues with crunching numbers in time, or can you give us a little understanding of that?
Sure, we do use MATLAB. That's one of the tools that we use. We also use a FEA program called COMSOL. I know a lot of people who do work in this area are familiar with that. And then a lot of it we just do sort of brutal computing. We'll set up just a traditional PC and do a lot of the number crunching there. And it's I'll say the data sets that we're looking at are not that large. They tend to be data that are produced in our system, so it's limited in that sense. And I think those computing tools are adequate for the application we have. I do think in the future, though, that's where this is all headed, right? I mean, as data sets get larger, of course, the ability to come up with predictive relationships is going to grow. So it will take more and more powerful computing means.
Yeah, we'll follow up with you on a hyperspectral imaging project that's going to have a very, very large data set. And Andrew, we can talk offline and meet up with Jerome about that, and then let the audience know what came out of those discussions for another podcast. That'd be exciting.
Absolutely. Jerome, because I already taken a lot of your time. We don't have much time left, but I wanted to ask you, and selfishly, because I'm asking you this because I want to know, but also for my nephew, because I didn't really know how to guide him. To create medical devices in the future, you can become a mechanical engineer, you can go into artificial intelligence, you can get a PhD. What would you recommend a young person who's interested in artificial intelligence in healthcare, interested in developing devices, interested in using AI to make the world a better place? What kind of trajectory would you recommend? Do you think someone even needs to go to medical school anymore for this, or what are your thoughts?
Well, I think it depends on how you want to make the contributions to that field. If you want to obviously make them directly, then medical school is a great way to go because you get the formal, training in that area that allows you to understand how these physiologic and anatomical processes interact. I think if you want to contribute to the field, let's say from a product development standpoint, then to me, the traditional engineering path is the right way. But I shouldn't say traditional because, again, I think, and again, I'll tie this into my Harvey Mudd education, which was multidisciplinary. I think that's the key to being effective in this field. Every product I work on, as I said at the start of this podcast, involves mechanical hardware, electrical circuits, computer analysis of routines, GUIs, displays. And if you're going to be an effective developer in this area, you really need to know how to traverse all those different subject matters. So I'd recommend a broad-based engineering background that will give you the capability of communicating in all these fields and being able to make contributions using these different technologies.
So in a mechanical engineering degree, AI is just going to become part of that degree, I guess is what you're saying. It's not like
that's correct.
The other, they're going to be hand in hand.
Yeah, I think they're being hand in hand because, again, you can run the AI routines, but you have to have a device that can collect the data, a device that can process the data in the right form, something that interacts with the patient. So you really have to master all these technical disciplines, I believe.
So for my last question, then I'll turn it over to Vincent to close it out. Do you accept internships of college students?
Absolutely.
Wow.
We certainly do.
Good.
I have an intern that's going to start in next week in about 5 days. So I'm looking forward to it.
So
it really ends up being bilaterally beneficial. We get some really bright young minds, and they get some good experience.
Fantastic. My sister's going to owe me big time. So Vincent, take it away, please.
Well, that's a good question. We'll get back to you about the internships too, Jerome. Maybe there's a way for us to help sponsor some kids, and
sure.
And you provide mentorship. So, Jerome, thank you for your time on our podcast. We'll follow up back with you, and we'll close out. Vincent Grasso, I'm social media director and director of strategy for our excellent journal. We are the only journal dedicated to all things AI in the surgical domain, with senior leadership via Andrew, and it's an exciting time for us all. So looking forward to seeing you again, and enjoy the holiday weekend.
Yes,
thank you.
As Vincent said, and I forgot to mention, but I always like to, we are the first journal dedicated exclusively to AI in surgery. So Jerome, hold on, I'll just stop the recording.